It's a pleasure to have Shlomo Razamat from Technion Haifa. And over to you, Shlomo.
Okay. Do you see the screen?
I see it.
Okay. So thank you very much for organizing this very nice meeting and giving me the opportunity to present this talk. So the title of my talk will be SQCD and a pair of pants. It will involve all the ingredients in the title of the workshop. It will involve quantum fields, geometry, and representation theory. And it is mainly based on a paper we wrote with my student Aviatar Sabak about a year ago. And also I will review in some detail a previous paper we wrote with Gabi Tzafrir, but it will cover roughly a number of works that we have put on the archive in the last 2 years or so. So let me start with the QFT part of the talk, okay? With the motivation of what I'm going to tell you, which involves quantum field theory. And let me mention that please stop me at any point with any questions you might have. So I do want to encourage questions during the talk. So the main motivation of this talk is to understand dynamics, or strong coupling dynamics, strong coupling effects of supersymmetric quantum field theories in 4 dimensions. In last 25 years or so, we learned a lot of very interesting facts about such quantum field theories. For example, these theories sometimes enjoy what is called IR dualities, infrared dualities, where you have 2 different UV QFTs, UV starting points, which flow to the same infrared fixed point. Okay, they are equivalent in the infrared. And here is an example of such a duality, a canonical example where you have an SUN SQCD with an F flavors, which is dual to another SQCD theory with N tilde flavors, where N tilde is equal to an F minus N, and a bunch of gauge singlet fields. Another type of interesting effects are conformal dualities, where you have some superconformal field theory, which has a parameter space, a space of exactly marginal couplings, which we'll call conformal manifold. And at some locus of this conformal manifold, you have a certain useful description in terms of, say, weakly coupled gauge theory, and then at a different locus of this conformal manifold, you can have a description in terms of completely different or just different gauge theory. And again, a canonical example is N equals 4 super Yang-Mills, where 2 descriptions are not don't look very different from each other, but nevertheless they are different. Another effect that will play a role in our discussion is emergence of symmetry in the infrared. So you can start from a CFT in the UV in 4 dimensions with a certain global symmetry, deform the CFT by a relevant deformation, flow to the infrared fixed point, and then the symmetry in the infrared might be bigger than the symmetry in the UV, okay, due to certain strong coupling effects. And what we want to understand is whether there is a certain organizing principle, a certain way of viewing or engineering these 4-dimensional supersymmetric quantum field theories, so that all these properties will be understood in some nice and general way. We have a collection of sporadic understandings, and some of these understandings we can organize into we can organize our thinking about this understanding in certain ways, for example, using brain constructions and so on. But we want something which will encompass, you know, most of this understanding in a uniform way. And here comes the role of geometry. Okay, so this is the part of the where the geometry comes into the game. And starting with this seminal paper of Gayotov, already from about 12 years ago, we know of a way to organize our thinking about 4-dimensional supersymmetric theories, but we do so by starting not in 4 dimensions, but rather in 6 dimensions. So what one can do is to start from some 6D CFT and think of it as a UV theory, and then deform it by placing it on a compact geometry two-dimensional geometry on some Riemann surface, and possibly turn on some background gauge fields, some fluxes supported on this Riemann surface. Then one flows to the effective four-dimensional theory, which one obtains by going to energies which are much smaller than the ones set by the size of this Riemann surface, and obtains this four-dimensional theory, which is now labeled by the Riemann surface which we started with, and by the flux that we put on the Riemann surface. Now, this particular theory might have different properties. It might be strongly coupled as CFT. It might be IR. It might involve some IR-free gauge fields. It might split into a product of CFTs. There might be some free chiral fields which decouple in the infrared. So there is a variety of different behaviors that can happen. An interesting question that we will ask in this talk, and which motivates this work, is whether there is a different theory that flows to the same CFT in the infrared. Okay, whether there is a theory which we can define directly in 4 dimensions in terms of weakly coupled fields, gauge fields, and matter fields, and such that certain relevant deformation of this QFT in the UV in 4 dimensions flows to the same theory in 6 dimensions. So this 4-dimensional Lagrangian theory will be labeled again by this geometric data, by the Riemann surface, and by the flux. Okay, such a 4D description might exist or might not exist. Okay, but the point is that if we find a dictionary between 6-dimensional flows and 4-dimensional flows in such a way, many of the strong coupling effects, such as IR dualities, conformal dualities, enhancements of symmetries, can be understood through this dictionary. Basically, because these 4-dimensional theories will carry with them this notion of geometry. This Riemann surface, the 6-dimensional theory was compactified on, the information about the 6D theory and fluxes and so on. Okay. This 4D description might flow to the same SCFT or might sit on the same conformal manifold as this SCFT. And in this talk, we will mainly at least most of the talk will mainly consider such Lagrangian constructions where this 4D Lagrangian directly describes this fixed point, that is, it sits on the same conformal manifold as this point. Okay, so there are 2 questions that we will ask. Question number 1 is, given a 6D SCFT and a set of compactifications on the Riemann surface, how can we obtain such explicit 4D Lagrangian descriptions, and whether we can do so? And the second question is, what type of physics follows from these geometric constructions of 4D CFTs? So before beginning the actual discussion, before starting the actual discussion, let me emphasize this point again. So there is one way in which we construct this 4-dimensional theory. So in this case, we start from a theory in 6 dimensions, and we compactify this 6-dimensional theory on a 2-dimensional surface and obtain a 4-dimensional QFT. So we flow across dimensions from 6 dimensions to 4 dimensions. And we are after an alternative description of the same fixed point or of the same conformal manifold, which starts directly in 4 dimensions. So we're after a certain infrared duality across dimensions. Okay, usual infrared duality in quantum field theory start in the same number of dimensions, say in 4 dimensions. But here we are after a duality which goes across dimensions. And this will be a main theme of this talk. Any questions up to now? Yes.
So it could also be that this second QFT that you are after also has a 6D description, right? Or a higher dimensional description.
You mean there is a flow to this CFT point before you do the deformation which takes you to this conformal manifold?
Yeah, I'm saying that from 6-dimensional there might be a way to understand why this second one is flowing to the same SCFT in 4D, right? But you are not trying to understand that.
No, we are trying to understand that, that also. So let me try to understand your question better. So there are 2 points here. One point is, how do we know, how do we derive this 6D, sorry, this 4D SCFT?
Yes.
And that I will address. Okay. And
Okay.
if I don't address, if I will not address it in a way that you will be satisfied, please ask me again. But there is another question that you can ask is, okay, there might be another 6D SCFT or another deformation of 6D SCFT, which will bring you directly to this UV fixed point. Okay.
That's correct.
And then deform this UV fixed point by some relevant deformation and flow further to this theory. This is also possible. There are, in certain cases, actually, we will discuss one example of this happening towards the end of the talk.
Okay, thank you.
But this is the crucial point. We want to develop a dictionary between 6D CFTs and these compact geometries and 4-dimensional theories. And once certain basic building blocks in this dictionary are derived, we can build anything we want by gauging certain symmetries, turning on relevant deformation, turning on vacuum expectation values, and so on.
Okay, thanks.
Okay. Okay, so to start this program, in this talk, we will consider very, very restrictive assumption. Okay, so in general, the problem with this type of a program is that the 6D CFT is strongly coupled. We don't have any useful descriptions to start with to understand fully what is the 4-dimensional theory one obtains. And for that reason, many times these 4-dimensional theories are called non-Lagrangian because the starting point is non-Lagrangian. We don't know of an explicit Lagrangian description in most of the cases. So this is a hard problem to understand. So in this talk, I will assume that this theory in 4 dimensions that you obtain in this geometrical engineering has a conformal gauge theory description. This is assumption which might be correct, might be wrong. This assumption in most of the cases is wrong, but for a particular class of examples that we will discuss, it will be correct. And from that starting point, we will be able to derive a lot of interesting results. Okay, so why starting from this assumption, restrictive assumption, is useful to us? And it is useful because making this assumption, one can write down a very simple algorithm to seek for such a cross-dimension dual of the given compactification. And here, let me slightly generalize the discussion, and let me assume that somebody gives me a certain 4-dimensional theory that I will call T1. It might be given to me by this geometrical procedure or something. Somebody just hands to me a Lagrangian for this 4D theory. Somebody defines to me this theory in some way. It doesn't matter in this way. And I will only ask this person to give me very limited information about this theory. For example, I will ask this person to give me the A and C anomaly, the conformal anomalies of this theory in 4 dimensions. And I will also politely ask for some protected information about this theory. For example, what is the conformal manifold of this theory? What is the dimension of the conformal manifold? What is the symmetry preserved on the generic locus of this conformal manifold? If one can give me the indices or some other supersymmetric partition functions, that will be also great. The anomalies of various symmetries on the generic locus of the conformal manifold. Okay, so this is the only information I will want to be given about this theory T1. And then I will ask the question, whatever this theory is, can I seek for a conformal dual of this T1? Namely, for a theory which is given in terms of free fields, free gauge fields, and free chiral superfields in 4 dimensions with exactly marginal deformations, such that this theory might be related to the theory T2 by tuning certain continuous couplings. Okay. And now the point is that if we assume that all the fields are free, that we are on a conformal, we are in the setup of having a conformal gauge theory, there is a very neat relation between the A and C anomalies and the number of vector fields, dimg, and number of matter fields, dimr, where R stands for the representation of the matter fields under the gauge symmetry, So there is this very neat relation, and it follows from this relation between A and C anomalies and Hooft anomalies of R symmetry, of the superconformal R symmetry that one generally has in n=1 CFTs. For free, if we assume that all the fields are free, their R charges are set to be, the R charges of the chiral fields are set to be 2/3. And thus, this relation simply gives us a relation between A and C anomalies and these dimensions of the gauge group and the representations. And again, the assumption of the theory being conformal is crucial here. So if somebody gives us A and C, we immediately can read off the dimension of the gauge group and the dimension of the representation of the putative conformal dual. These numbers might turn out to be fractional. And if they turn out to be fractional, then this conjecture is wrong, okay? Then there doesn't exist a conformal dual, gauge theory dual of our theory. If these numbers are integers, what we can now do, we can list all the possible gauge theories with this dimension of the gauge group and this dimension of the representation, and see whether we can construct a conformal gauge theory with this conformal manifold, with the indices that are predicted by explicit computation in theory T1, the anomalies, and so on. If we find a theory out of this finite list of theories with this gauge group and this dimension of the representation, we have a conjectured conformal dual. And then we can test it in a variety of ways, which will depend now on specifics of the given construction. Okay, is this algorithm clear? Okay. Let me give an example, which is a simple example unrelated to the general geometric construction that we will discuss in a moment. So let's say that somebody gives us this theory T1 here, which resides on some conformal manifold. And this theory T1 is simply a G2 SQCD theory with 3 fundamental fields in the 7-dimensional representation and 1 field in 27-dimensional representation. One can actually show that this theory is conformal by itself. It has a 3-dimensional conformal manifold. The global symmetry on this conformal manifold, on the generic locus of this conformal manifold, is SU2. At the free point of this theory, the symmetry is SU3 rotating the fundamentals, and there is another non-anomalous U1, but going on the conformal manifold, this SU3 is broken to an SO3 or SU2 subgroup. One can compute the Hooft anomaly between R symmetry and this SU2 symmetry and get this number. One can compute indices, whatever you want. This is a usual gauge theory, so whatever protected information you're interested in, you can compute. For example, there are 7 relevant deformations, which are in this representation of the preserved SU2. And then one can ask whether there is another different gauge theory description of the same theory somewhere else on the conformal manifold, and how to find it. So we can just apply the algorithm that we have discussed. So in this case, this theory is conformal by itself. So the dimension of the gauge group and the representation of the dual should be exactly the same as these dimensions, the dimensions of this gauge theory. So in this case, the dimension of the group is 14. We need to build 14 from dimensions of simple Lie groups. And there is only one way to do so in this case, which is not G2 by itself, and it is in terms of 2 SU2s and SU3s. So we take 2 SU2s and then SU3 gauge group. And then we try to find 48 chiral fields and put them into representations of these 3 gauge groups in such a way that the theory will be conformal and will satisfy the same properties as here. And it is not very hard to find such a gauge theory. This gauge theory is drawn here, and it has exactly the same properties. So A and C anomalies of this theory are the same as A and C anomalies of this theory, just by construction, because it is a conformal theory and it has this number of these dimensions of the gauge group and of the representation. This theory at the free point has a large symmetry, for example, SU3 rotating these fields to SU2s and a bunch of U1s. But again, once you go on the conformal manifold, you find that the dimension of conformal manifold is 3, and the symmetry which is preserved is SU2, and this SU2 is embedded as an SO3, like 3 goes to 3 of this SU3, And the diagonal combination of this SU2 embedded in this SU3, and the SU2s which rotate these two fields. You can these two pairs of fields. You can compute the 't Hooft anomalies and find exactly the same number. You can compute relevant deformations and indices and find that all the information of these two theories actually agrees. So here is a picture. Here we have a conformal manifold, which is three-dimensional. There is a point where we have this G2 gauge theory description, and conjecturally, there is a different locus on this conformal manifold where we have a quiver theory description of the same theory. Okay, so this is how this algorithm works in this simple example. One can try to construct many examples of such dualities. Any questions?
So typically there would be multiple of these, right? So in
well,
this...
you are right. So in general, and we will see an example of that in a moment, you are absolutely right. You write a finite list of theories which have, say, this dimension of gauge group and dimension of representation, and out of which most of the times none will work. Okay, so you will not find a dual. In some cases, you will find one. In some cases, you will find more than one, which will satisfy all of these properties. Okay, so it's not it's not just a duality. It can be triality or whatever.
Correct. Thank you.
Okay. But the point is, if a conformal dual of a given theory exists, you are bound to find it using this algorithm. And if there are many such dual theories, you will find all of them.
So
okay.
Just something related. Yes. So if you had included, let's say, asymptotically free theories as well.
You mean theories which flow to this theory.
Yeah.
Then this restriction on coming from you know, the R charge of fields being free doesn't hold. So the game is much more open. Like you can have the space of parameters is much bigger. You can actually do that, and people did that. You can, for example, assume that some chiral fields have R charge 2/3, some have 1/3, and then you still have a constrained game to play, and you can scan the all the possibilities and maybe find some duals. But again, once you move from this assumption of conformality, you increase the number of possibilities, and and in general, the R charges won't be even quantized in a nice way, so the game will be much more complicated.
Okay, Aswin has a question, so
sure.
Maybe Aswin, you can ask.
No, I was just counting naive dimensions of the conformal manifold. So I would have naively thought T1 had a conformal manifold that's two-dimensional.
Well, you probably counted. So let me count it. Let me perform this counting here. So what are the marginal operators? So there is this field Q tilde. So the Q tilde to the 3 is marginal, but actually there are 2 of them. So maybe this is the one you missed. There are 2 different, if you wish, index contractions, which give 2 independent marginal operators, which are in Q tilde cubed, which have the form of Q tilde cubed. Okay. Then there is a baryonic operator, okay, which is just Q cubed, which is +1. And then there is an operator of the form Q tilde Q squared, which is of which there are 6 different operators, okay, which is you symmetrize the indices of Q squared. So naively, you have 9 marginal operators in addition to the gauge coupling. And then what happens is that the claim is that the symmetry is broken, the global symmetry is broken down to SU2. And if you remove the conserved currents from there, you will obtain only 3 marginal operators, 3 exactly marginal operators. Does this answer your question?
I see. Okay. So the claim is there's an identification of conformal manifolds between T1 and T2?
That's right. What is the identification? We don't know. Like there is a 3-dimensional conformal manifold here, okay, and a 3-dimensional conformal manifold here, okay. But what is exactly the map, like tau goes to -1 over tau of n equals 4, we don't know. Okay, it is a very interesting question. How you exactly map, weak coupling, weakly coupled cusp here to weakly coupled cusp here, we don't know. Okay, we assume that there is some map. Okay, how
Well,
it goes, it's yes.
Even, I mean, there's a sort of distinguished subspace of the conformal manifold of T1, namely where you just vary the gauge coupling and keep the other marginal operators that you described set equal to 0.
That you cannot do. This is an marginally irrelevant deformation.
Oh, excuse me. Sorry, you're right. I'm sorry.
So,
I take
there
that
is
back.
no
So that's,
obvious, nice direction.
no, you're right. You're right. Sorry. That's
okay. So at least maybe there is a nice direction, but I don't know of it. In principle, all the directions look rather complicated. There is a subspace here which is two-dimensional, on which you preserve more than SU2 symmetry. Basically, all the SU3 symmetry is preserved. But that direction is not, it might be not, this theory might not be on that direction and so on. There is no reason it will be on. Okay.
Yeah, so that's what I was looking for, a subspace where you preserve more of the global symmetry.
But the symmetry of this theory is so different at the free point than this one, so it's not clear what you should look for. Okay. But in principle, you're right. There might be a nicer direction. I just don't know of it. Okay. So this was the explanation of the algorithm. So now let me apply it in this particular case. So again, we will start from some 6D CFT, put it on some Riemann surface. We will obtain some 4D theory about which we know some protected information such as anomalies, and we will assume that this theory is described by a conformal Lagrangian, and we will look for this conformal Lagrangian. So the particular case that we will discuss is to take in the 6D CFT to be what is called rank 1 E-string theory, and compactify it, place it on a closed Riemann surface of genus G bigger than 1, and not turn any flux for the global symmetry of this theory. The global symmetry of this theory in 6 dimension is E8, so we don't break this E8 by turning on some fluxes on the Riemann surface. We keep it, we just compactify this theory on closed Riemann surface. Okay? So this is some strongly coupled SCFT, and some things about this SCFT are known. For example, one can compute the 8-form anomaly polynomial of this 6D SCFT. This was done, I think, first time by Omori, Shimizu, and Tachikawa several years ago. And then from this 8-form anomaly polynomial, you can compute the anomaly polynomial of the 4D theory you would obtain by compactifying on this Riemann surface, just by integrating the anomaly polynomial. And then you predict these A and C anomalies of the 4D theory you would obtain in this compactification. Now, from the relation of A and C to the dimension of the gauge group and dimension of the representation, you arrive that the dimension of the gauge group and dimension of representation should have these values. Again, assuming that there is a conformal dual of these theories. Now, notice that these theories are, these numbers are integer, are not fractional. So this is a sign that maybe there is such a conformal description. And in fact, you can easily find it. So in the simplest case, when you take G equals 2, the dimension of the gauge group is 16. So there are various ways to build 16 using dimensions of simple gauge groups. One simplest way is just to take 2 SU3s. And in more generality, for genus G, you take 2G minus 2 SU3 gauge groups. And then you have to take this number of chiral fields. And it is very easy to find a conformal gauge theory with this number of gauge groups and this number of matter fields, which will be a putative dual of a compactification of an E-string theory on this Riemann surface. So it's a very straightforward computation to perform, and in this case it works. So here this theory is conformal. Notice that you have SU3 gauge nodes, and each gauge node has an F equals 9. It has 9 fundamentals and 9 anti-fundamentals. This SU3 with 9 flavors is at the upper edge of the conformal window. Typically for number of colors which is not 3, such theories are infrared free. but for a number of colors being 3, you can turn on baryonic superpotentials, and this builds for you a conformal manifold for this theory. So this theory, for this theory, you can turn on any baryonic superpotentials using these chiral superfields, and you can also turn on superpotentials corresponding to the triangles in this quiver. So anything which is consistent with free R charges. So the claim is that compactification of E string on this surface will give you this SCFT. Okay. So let me discuss what is the evidence beyond the matching of A and C anomalies. So this was derived just by matching A and C anomalies between these two theories. So you need to say something more. So here is the picture. So we start from a 6D compactification on some Riemann surface, closed Riemann surface, and obtain predictions for this theory T1. And this theory T2 is given by this quiver theory. And now we need to match various properties of these two descriptions. So the symmetry of the 6D theory is E8, as we already mentioned. And we preserve that E8 symmetry naively when we compactify to 4 dimensions. We can compute the dimension of conformal manifold of this theory. We expect it to be given by the number of complex structure moduli of the Riemann surface, which is 3G minus 3, and flat connections for this E8, with number of which is G minus 1 times the adjoint of E8, which is 248. One can show that on generic locus of the conformal manifold, you completely break the E8, so the symmetry on generic locus is empty, there is no symmetry. If you do preserve E8, this is the 't Hooft anomaly that this E8 should have. Now, you can study the conformal manifold of this theory. As I mentioned, you can build a marginal operator using triangles and baryons. So the triangles, for example, you can, turning on this particular combinations of these marginal operators, you can preserve an SU9 symmetry, for example, just turning on triangles which preserve this SU9. You identify all the SU9s that you can have here at the free point, and only baryonic operators which correspond to the external edges of this quiver. And then in terms of this SU9, for example, these baryons will be in 84-dimensional representations, and the triangles will be in 80-dimensional representations. So when you will compute the number of exactly marginal deformations, you will find exactly this number, and not just the number 248 here, but you will find that the representation in terms of this SU9 of these marginal operators will be 80 plus 84 bar plus 84, which is the decomposition of E8 into the representations of the SU9 maximum subgroup. Okay, so the picture here is that compactifying from 6 dimensions to 4 dimensions, you get some huge conformal manifold. Somewhere on this conformal manifold, you have an E8 symmetry preserved, actually on this locus of the conformal manifold. Then there is this gauge theory description, and this can preserve an SU9 symmetry. And this SU9 symmetry can be further broken to 8 U1s. And you can actually go along these directions, preserving U1 to the 8 between the E8 preserving conformal manifold and SU9 preserving conformal manifold. And you can compute the 't Hooft anomaly of SU9, and because the embedding index of SU9 in E8 is 1, you exactly find the same anomaly. You can and then you can perform some more finer checks using some things that we know about compactifications of E-string theory, which were derived before, and again find agreement with previous results. So again, the claim is this is the theory which is obtained in this compactification. And if you wish, this is an example of an emergent E8 symmetry. There is no E8 symmetry in this theory, but somewhere on the conformal manifold of this theory, we expect E8 to emerge. Okay, any questions? Yes?
Jacques?
Yeah, sorry, I was slightly confused. Shouldn't flat connections lie in the Cartan? So I'm confused why it's 248 and not 8.
No, you are thinking about the torus. This is a generic surface. Okay.
Fair enough, but still, I mean, the condition that the thing is flat means that the holonomies, I should be able. Shouldn't the holonomies all commute? I don't. That's why I'm confused.
No, sure.
Well, it wasn't a torus question. The Jacobian, I would have thought would be G minus 1 times the rank, not the dimension. I'm confused.
I think if you look on the torus, you're right. You only have this, you only turn on for, maybe it's a little bit confusing. It's true that what happens on the, say if you are on a torus, and then you can break this non-abelian symmetry into the cartan, and you cannot break the cartan. Okay, that's a statement about the torus. On a higher genus surface, you can break the symmetry completely. You can break the non-abelian symmetry completely. I don't have a very a simple argument why is it true, but maybe we can discuss later.
Yeah. Okay. I mean, I guess I'm struggling to understand the description of flat E8 bundles on the Riemann surface, where the moduli space is
turn on. So there's
yeah, I know, but shouldn't the holonomies commute? I mean, I would have thought it was G times the rank.
Be consistent with the cycles, that's what you should. That's what you should.
We can discuss it later.
Okay.
Yeah.
Okay. So this is a picture. This is a picture of this duality, and now I come to a question that I was asked before. So we have derived one particular example of this duality across dimension, and maybe there are more. Okay. And here is an example of where we do find more dualities applying this algorithm. So let us look at a particular case of genus 2. Okay, so this is the theory we have written before, specialized to the case of G equals 2. I don't write it in terms of a triangle. I write it specifically in this form to make a point, but you should have in mind turning on any superpotential which is consistent with the R symmetry of this theory. So this is the theory T1 we obtained by compactifying from 6D to 4D. We have claimed that this is a dual of the theory somewhere on the conformal manifold, and we're asking, can we win this game in some other way? Can we find another conformal theory description? And it turns out that we can. For example, here is a different conformal theory that we can write, which has exactly the same properties. So again, we have to have the number of vector fields to be 16 in this case. So we have 2 SU3s, and we have to have 81 chiral superfields. So here they are built by these bifundamentals and by these fundamentals. And here we'll have bifundamentals, fundamentals, and 6-dimensional representations. Okay. So this theory and this theory have the same A and C anomalies, the same conformal manifold and the same indices and so on. So the claim is that there is another locus on this large conformal manifold where the effective description and the useful weakly coupled description is in terms of this conformal gauge theory. Okay. Now, what is nice about these two descriptions that there is a natural geometric interpretation of these two descriptions. So here I draw the same quiver theory. I just separate these 3 bifundamental fields, and these 9 chiral fields just come on the right. So there is a natural way to associate the genus 2 surface to this picture. In the same way, there is a natural way to associate the genus 2 picture to this theory. Now, again, we split this 10 into a 9 and a 1 fundamental. And then we remember that if we take 3 times 3, 3-dimensional times a 3-dimensional fundamental representation of SU3, we obtain a 3 bar and a 6. So that's how I want to think about the additional fundamental fields entering this 10 and this 6-dimensional representation. So you can draw the same picture, the same quiver theory here in this way. And then you can think of these two different looking quiver gauge theories as just two different pair of pence decompositions of the same Riemann surface. So either we take two three-punctured spheres and glue them in such a way, or glue them in such a way. And this is the geometric interpretation that we want to make, to give to these two different gauge theory descriptions. Okay, and I will spend the rest of the talk making this claim precise and deriving certain facts from this claim. Is this clear?
So sorry,
yes.
Quick question. So this particular Riemann surface,
yes,
is this the one that you use to get T1 from 6D, or is it something just?
Yes. So we take we take the E string on a genus 2 surface. Okay, and this is the quiver theory we obtained before. It's this theory, but specialized to G equals 2.
Okay.
You have only two SU3 nodes, and that is the theory that we get. Now we are asking ourselves: is there another conformal gauge theory which has the same A and C anomalies, the same number of matter fields and gauge fields, which will give the same type of protected information, same indices, same anomalies, and so on? And in fact, there is. This is a different description. Okay.
Okay.
So this is naively, these are two different theories. Okay. But the claim is that they are dual to each other. They sit on two different cusps of the same conformal manifold.
Okay. But does that tell you a little more about the conformal manifold of the dual?
It tells you that we expect to have such a weakly coupled cusp. Where exactly it is on this huge conformal manifold, we don't know again.
Okay. Thank you.
Okay. Okay. So what we will do now, till now we have discussed compactifications on closed Riemann surface, and now I want to break this Riemann surface into punctured Riemann surface, into gluing 2-3 punctured spheres. Okay. For that, I need first to discuss what are punctures and how to think about punctures. So will do it in a very caricature way, very quick way to get to the point, and then we will get to actually splitting these genus 2 surfaces given by these quivers into a pair of pens, into 3 punctured spheres. So the 6D theories are strongly coupled as CFTs. If we want to put a puncture on the Riemann surface, it a priori is a complicated problem. We need to understand what does it mean to have a puncture and so on. So one way to think about it is to take this Riemann surface with a puncture, elongate the region around the puncture into a cylinder, and consider first compactifying on a circle to 5 dimensions. In certain favorable cases, if you take a 6D CFT and compactify it on a surface, you get a gauge theory description, a gauge theory which is UV completed by the 6D CFT. For example, a very familiar case is if you take a 2,0 theory and compactify it on a circle, say the 2,0 of type A, you get an A-type maximally supersymmetric Yang-Mills in 5 dimensions. Okay. So let us call the gauge theory in 5 dimensions as gauge symmetry in 5 dimensions as G gauge 5D. And then now we have a gauge theory description in 5 dimensions in terms of fields. We can ask what happens at the boundary, what happens at the puncture. Okay, so we need to give certain boundary conditions, and there is a preferred boundary conditions, the condition that we can put at the boundary, which is usually called maximal boundary condition or maximal puncture, when we give Dirichlet boundary conditions to the vector fields, and then whatever is needed to preserve some supersymmetry for other fields. Okay, so what this does, it freezes the 5-dimensional gauge symmetry in the bulk of this space on the boundary. And on the boundary, for each puncture, we get a new factor of flavor symmetry, which is equal to the 5D gauge symmetry. Okay. There are additional types of natural operators that we can identify. For example, in the case of 2,0 theory, the supersymmetry that we can preserve by such boundary conditions is n equal 2. This n equal 2 if we have a global symmetry comes with what is called moment map operators, and these moment map operators can be identified with certain fields in 5 dimensions which receive Neumann boundary conditions, which are in the joint representation of this 5D gauge symmetry. Now, in the case of E string that we are discussing here, again, we can, going to 5 dimensions, there is a 5-dimensional gauge theory, and it is SU2 gauge theory, but with 8 fundamental hypermultiplets. And we can again define a maximal puncture in this case, and this maximal puncture will come with SU2 global symmetry. And then giving Neumann boundary conditions to certain fields, we will obtain that we expect to have an octet of chiral operators in 4 dimensions, which are in fundamental representation of this SU2. Okay, so this is very analogous to what most people know about class S constructions, which are just compactification starting with 2,0 theory. Okay, so this is the puncture. The puncture in this thing should have an SU2 symmetry, and it should come with an octet of chiral operators in the fundamental representation under the puncture symmetry. And this picture generalized to any 6D CFT that you can start with, and such that on a circle you have an effective gauge theory description. Now, given a punctures, we need to understand how to glue 2 surfaces along punctures together. And there are 2 basic operations that one can perform while gluing. So gluing corresponds to, in a sense, undoing the boundary conditions at the boundaries, joining the 2 surfaces at the boundary, and undoing the Dirichlet boundary conditions, so on. So one thing one needs to do is gauge the symmetry which we have frozen on the boundary. So in our case, we will need to gauge this SU2 symmetry. And the other thing we will need to do is identify or reintroduce the fields which we have given, the chiral fields that we have given Dirichlet boundary conditions to. So there are 2 ways to do it. One way we call S gluing, another phi gluing. So in one way, we identify the fields that we given Neumann boundary conditions with fields which we have given Dirichlet boundary conditions here. In field theory, this will be done by just turning on such a superpotential, coupling the moment maps of the 2 theories, of the 2 copies of the theories to each other. And again, I will call these octets of fields, fundamental fields, as moment maps by abuse of notation in analogy to 2,0 compactifications. These are not real moment maps. We only preserve here n=1 supersymmetry. This superpotential will identify the symmetries of the 2 copies of the theories we glue with the conjugation. That's what I write here. What it basically means is if here we have representations under the puncture symmetry or under any symmetry which is R, here we will have naturally conjugated representations. So that is what this statement means. And if we associate flux F to this theory, and we glue the same type of a theory to this one with this as gluing, the flux that we'll associate to this other copy will be minus the flux. And then there is this other gluing that we can perform where we can we reintroduce the fields that we given Dirichlet boundary conditions by hand, just adding these chiral fields, and this will be denoted by this field phi with this superpotential in the field theory. And this is the usual, say, n=2 gluing that you know from class S, and this is n=1 gluing in class S if you want. Okay, there is a more general, there are more general possibilities which exist in E string. You can do combinations of S and phi gluings. We will not get into this here. Okay, any questions about this? Okay. So now, before going back to our E string compactifications, let me remind you a simple fact. Maybe one of the basic examples of Cyberduality is discovered many, many years ago. And we will use this fact with the definitions of the punctures that we have defined to split our genus 2 surface in 2 pairs of pans. Now, remember that SUN plus 1 SQCD with an F equals N plus 2, with number of flavors being one more than the number of colors, is claimed to flow in the infrared to a simple West-Zumino model. So a gauge theory will flow just into a collection of chiral fields coupled through a superpotential. So this is the quiver diagram of this gauge theory, and this is the West-Zumino model. So these fields correspond to the mesons in this quiver, and these are the baryons, and then there is some superpotential coupling them. There is a triangle, and there is a higher order superpotential, which takes this field to the power n plus 2, basically. Now, this, what we have in our quiver, this is a quiver which corresponds to the genus 2 compactification. We have exactly these types of triangles when you take n to be equal to 1. Okay? So what we will do, we will look at this quiver, and we will substitute in this quiver these types of triangles with the Cyberdual theories in terms of a gauge theory. Okay, so we'll have nodes here, we have edges here, and we will replace these edges with nodes on them. Okay, and in this way we will obtain something which will look exactly as gluing of two three-puncture spheres, as we will immediately see. So that's what we do. So we take, say, one of the triangles appearing here, and we replace it with SU2 with 3 flavors. So when we replace a triangle, this 9 becomes an 8. Okay, and then we can do it for another node, and this 8 will become a 7, and then yet another edge. Sorry, not node, but edge, and this 7 will become a 6. So these two theories are dual to each other due to the simple Cyber duality. They are IR dual to each other. But now this theory has a natural interpretation. You see, it is just a gluing of 2 pieces together. And by gluing, we are gauging SU2 symmetries exactly as we expect to be doing when gluing 3 punctured spheres together for the E string. We have this SU2 symmetry. And thinking a little bit more about it, what we are doing the S type of gluing here. We don't introduce any of these fields phi that I mentioned. So the geometric picture of here is that we are taking a certain 3-punctured sphere, which is associated to some flux F. We're S gluing it to the same type of theory. So that theory has a flux which is minus F, and we obtain a compactification of this genus 2 surface with 0 value of flux. And then the theory which corresponds to the 3-punctured sphere is just half of this picture, which is just SU3 and F equals 6 SQCD. Any questions about that?
So then is this a way of also including theories which are not conformal within the duality?
That's right. So in this way, we started, all our discussion was conformal. Okay. And here in this procedure, the point of the conformal insistence on conformal symmetry, on conformal description, was to find a theory, to find, a way to look for a Lagrangian theory we obtain in compactifications. And we restricted to compactifications on closed Riemann surface with 0 flux. And we succeeded in that goal. But now we want to break these closed Riemann surfaces into 3 punctured spheres, possibly with flux. And these theories by themselves don't have to be conformal, and the gluing doesn't have to be conformal. But this theory would flow to a conformal gauge theory. It is some UV theory which flows to some fixed point, which so happens has a conformal gauge theory description.
I see. But can one make a more systematic statement about, exactly what kind of theories might flow to this in the IR? Is there a possible classification?
Oh, no. Well, maybe there is, but I'm not attempting to do that. You say what are all the possible IR duals of this theory? That's correct. Yes, for example. Yes, it's a very interesting question. I'm not attempting to solve it, to give an answer to that question. Yeah. Okay. There might be some mileage to be obtained by thinking about this question, definitely, but I don't know the answer. Okay. In a sense, we will, by our procedure, we can discuss it after the talk. We can find infinitely many duals of this theory. in doing certain procedures. But again, this infinitely many will not be all of them.
I see. But infinitely many up to cyberdualities, no, right? Because you probably could
for example, you can well, up to some dualities. Yes. For example, you can take any thinking abstractly. You can start in 6 dimensions with a 3-punctured sphere and put here any flux you want.
Okay.
And then minus that flux here. Okay. So abstractly, you get immediately infinite number of dual descriptions,
right?
Depending on this flux. Okay.
Yeah.
This theory will correspond to a particular value of flux, which we'll derive in a couple of slides. But it's not a parameter here. It's some value of flux which we need to understand what it is, and we will do it in a moment.
Okay.
Okay. How much time do I have?
You have about 10 minutes.
Okay. So great. So I'm close to the finish line. Okay, so this is the trinion then. That's what we obtained. So the compactifying on a 3-punctured sphere with some value of flux to be determined on the next slide gives you just SU3 and F equals 6 SQCD. That's the basic claim. This theory has an SU6 times SU6 times U1 baryonic global symmetry. We think of one SU6 symmetry by splitting it into 3 copies of SU2. We have additional 2 U1 symmetries which are obtained in this splitting, which together with this U1 baryon give you 3 factors of U1 symmetry, and there is additional SU6 symmetry coming from here. So in total, we have 3 SU2 symmetries that we would associate to the 3 punctures, and additional SU6 times U1 cube symmetry, which is a rank 8 symmetry, which we will want to think of as a subgroup of E8. Okay. Now, what are the moment maps? So for each puncture, we have we are looking for an operators with a certain value of R charge, which turns out to be 1. This is the R charge of this moment map operators, which are in. So this operator should be in the fundamental representation. So how we build them? We have 6 mesons, which are built like that. Say we are looking on this puncture, and then we have 2 additional operators, which are baryon. So take this field once and this field twice, or this field once and this field twice, and you get 2 additional operators with R charge 1, which are in the fundamental representation of this puncture SU2 symmetry. So we have an octet of moment map operators. 6 of them are mesons, 2 of them are baryons, and all of them are in the fundamental representation of the puncture symmetry. Okay, so this is the basic claim. So now what we did, we took the genus 2 surface with 0 flux, we split it into 2 3-punctured spheres, such that one 3-punctured sphere has flux F, another has flux minus F, and we got a total flux which is 0. But now we can combine the 2 3-punctured spheres with phi gluing. In that case, we just add up the fluxes of the 2 copies. Phi gluing has additional fields which we introduce when we combine things together, so it's a different theory. It's a well-defined field theoretic construction. So for example, we can compute the A and C anomalies of this field theory that we obtain in 4 dimensions and ask ourselves, is there a compactification on a genus 2 surface of E string with some value of flux which gives these types of anomalies? And it turns out that there is such a compactification. And in that compactification, we give a 1 unit of flux to a U1 inside E8, which breaks E8 to E7 times U1 subgroup. Okay, and if you do that, you can obtain exactly these types of anomalies. Okay, and the breaking of E8 into the subgroups that you see in the Lagrangian for a 3-punctured sphere is as follows. So there is this breaking of E8 to E7 times SU2. We give a flux to the Cartan generator of this SU2, and then we break this SU6, this is 7 into SU6 times SU3. This is the SU6 you see in the Lagrangian, and the 3 U1s that we see in the Lagrangian are the Cartan generators of this SU3 times SU2. You can compute, for example, the indices for these theories obtained by phi gluing the 3-punctured sphere. So here is a genus 2. Here I give an answer for general genus. And you see that the symmetry appearing in the index is 7 times U1. So this is an independent, non-trivial check of this identification of this 3-punctured sphere corresponding to a flux in U1 breaking E8 to E7 times U1. Okay, so a very particular value of flux. Okay, now having this three-punctured sphere, we can build a lot of theories with various fluxes, and I will not go into it, but there is a lot of fun that can be played here. Any questions about this? Okay, so the final comment I want to make is, so we had the QFT discussion, the geometry appeared, and now I want the representation theory and or group theory to appear in this discussion, although of course we had representations and group theory till now, but let me go a little bit more into it. So we have discussed that we can compactify this 6D theory on a surface with some value of flux, and we have an example of a compactification by now. But now let us think more abstractly about this compactification. So we have a rank 8 symmetry in 6 dimensions, C8, and we can give fluxes for any abelian subgroup of this C8. So in principle, we can choose 8 U1 symmetries inside E8 and give different values of fluxes supported on the Riemann surface for these 8 U1s. We also have 8 moment map operators. If you look at the charges under various symmetries of these moment map operators, they are all differently charged. They are charged under different symmetries. So one basis of U1s in which we can discuss this problem is just the basis of U1s under which each moment map is charged. Okay, and in this way we obtain a vector of fluxes, an octet of fluxes which parameterizes this theory. Okay, and it so happens if you do this computation for the three-punctured sphere that we obtained, taking any one of the 3 punctures, all of them appear, the 3 of them appear very symmetrically. The vector of fluxes that you obtain in this way is given here. So 2 U1s get flux -1 and the rest get flux 0. Remember that there is this natural splitting into 2 and 6. 6 of the moment maps are mesonic and 2 are baryonic. So this is the origin of this asymmetry. Now you can ask whether this flux preserves E7 times U1 to be consistent with what I told you on the previous slide, and indeed it does. The way to check what type of symmetry this flux preserves is just to take the roots of SO16 and the weights of spinorial representation of SO16 and find the ones which are orthogonal to this vector. And doing this computation, you find that the number of orthogonal weights, spinorial weights, and roots of SO16 exactly matches the 7 times U1 preserved symmetry in this case. Okay, so with this understanding, we can consider the following game. So we understood how to glue surfaces together to form a higher genus surface. And we understood what are the punctures. Now I want to ask the following question. Say I tell you what is a compactification on a closed Riemann surface with some type of a puncture. And then I want to remove that puncture from the surface. Is there a field theoretic operation which does that? And there is such an operation. We have these moment map operators which are charged under the puncture symmetry, and we can give a vacuum expectation value to moment maps, to these moment map operators. And there is a very particular procedure of giving a VEF to a component of the moment map operator, introducing certain chiral superfields with certain superpotential. And the claim is that doing so, we just remove the puncture and we obtain a theory corresponding to a surface with the puncture removed, but with the flux shifted by the certain amount. And the shift in the flux is for the U1 under which the component of the moment map which received the VEV, the shift of the flux is for the U1 under which the component we gave a VEV to is charged. Okay, so now we can play this game of closing punctures in various ways and shifting the fluxes. For example, we can start from our 3 punctured spheres and close one of the punctures to obtain 2 punctured spheres. We have 2 types of operations we can perform. We can give a VEV to a baryonic moment map operator, and then we will obtain this value of flux. Giving a VEV to a baryonic operator, we completely Higgs the gauge group, so we obtain certain West-Zumino model, which we can explicitly compute. This flux again preserves E7 times U1. We can give a vacuum expectation value to a mesonic moment map operator. We obtain this value of flux, and this preserves E6 times SU2 times U1 symmetry. The mesonic VEV will Higgs SU3 down to SU2, so not completely Higgs it. We'll obtain a different theory. So this theory will correspond to a two-punctured sphere with such a flux, and a certain West-Zumino model will correspond to a two-puncture sphere with a different value of flux, preserving the symmetries. And if we glue, say, these two-puncture spheres, these tube theories to tori, we expect to explicitly see the symmetries at least somewhere on the conformal manifold. So here is an example of a torus theory when we combine these two puncture spheres, preserving E7 times U1, and we expect this theory to have E7 symmetry, and this theory will have E6 times SU2 symmetry. So again, there is a lot of games to be played here by taking different theories corresponding to different surfaces and different values of flux. And the important thing is that if the combined theory has certain value of flux, it doesn't matter in which way you constructed that theory, in which pair of pants decomposition, what are the fluxes of the different ingredients. If the final parameters parameterizing the surface are the same, the theories should be the same. They should be dual to each other. So in this way, you can engineer a lot of dualities. Some of them are new, some of them are just vanilla Cyberdualities. Okay, so let me finish. I'm going slightly over time. So this is the picture. So what we have discussed, we have started from E-string theory. We have discussed how to compactify it on a Riemann surface with flux. We did it in a certain way, going first through the conformal construction and then breaking into a pair of pants. And we constructed a dictionary between the 6D theories and 4D compactifications. And in this way, we can generate a lot of examples of enhancement of symmetry and IR dualities. Okay. So this is the main point of this talk. Just to mention before I finish, this discussion was for E-string theory, but you can generalize it to a sequence of 6D theories. And for example, for what is called minimal Dn plus 3 Dn plus 3 conformal matter, and there you will obtain, instead of SU3 in the middle of conformal window as a 3-punctured sphere, you will obtain other types of SQCD as 3-punctured spheres. If you, in the question section, I can tell more about it. So this is the summary of this talk that I want to give, a take-home message that I want you to remember. So in the end of the day, SUN SQCD in the middle of the conformal window can be engineered in the 6D types of constructions as compactifications of D-type conformal matter on a 3-punctured sphere, and we explicitly discussed the case of the E-string. Dualities of these theories in 4 dimensions are related to the action of the Weil group of the 6D symmetry group. In the case we discussed in detail, that was E8. The generalization is to SO4n plus 12. There are dualities which are related to pair of pants decompositions we have seen. There are other dualities in 4D which are related to 5D dualities, and here is an example, and this I didn't have time to discuss at all. Many known and new looking dualities can be obtained in this way. There is a lot of interesting 4D dynamics that can be encountered in this way, and so on. One thing I want to mention, that there is a more systematic way to obtain the results I have obtained by studying interplay between 6D RG flows and 4D RG flows, not going through this conformal assumption that we had in the beginning. Let me skip this slide and leave you with this more philosophical outlook. Thank you very much for your attention.
So I wanted to return to conformal dualities that you started with.
Yes.
So to briefly summarize, we wanted a pair of theories where the dimension of the conformal manifold was the same, the global symmetry was the same, A and C were the same, and the Tuft anomaly between the R symmetry and the global symmetry agreed.
All the
Right.
Tuft anomalies, like in the cases we have discussed, these were the only anomalies. But say if you have a billion symmetries, you would have, say,
But you'd have additional ones, right? Okay.
and all the indices, like everything you would match.
Oh, so you can also compute the indices and
well, if
show
you
that
have
those are-
like if you can on both sides compute the indices, they should match. Not always you can. Okay, so in the case of compactifications from 6 dimensions, you can predict the number of relevant operators and marginal operators, and these
Sure.
things you can understand from gauge theory description. So you match them. If there would be a way to compute the full index, it also should match. Like anything which is protected, right, which is independent of the location on the conformal manifold, should match.
Well, that last point was the one I was gonna ask about, because if we just take the data that I just listed, that's of course not sufficient, and we know counterexamples of theories where all of those data agree, but the theories are definitely different.
I completely agree. So this is disputative here. So once you have found these candidates for duals, you need to perform more checks, and these checks can fail. Okay. So, for example, in this case of this duality, you can compute everything basically. And as far as we,
so do you have examples where the additional checks fail?
Additional checks to these ones. Not here, but I can easily, for example, I have examples where some of these checks fail. Some not fail, but some do not fail, but some fail. For example, here it's easy to construct in this example. Just you see these two fields are oriented in the same way. Okay, just orient them in the opposite way. You still get a theory with vanishing beta function and so on, but it is different. Okay, it has the same A and C as this one and as this one, right. A different theory. But I agree with you. Even if I match everything here, it still might not be dual. For example, you might have different global structure of the flavor symmetry group and so on.
Right. Yeah. So that's one particularly sensitive test, but determining the global form of the flavor symmetry group can be tricky.
Yes. So that is absolutely true. And, this has to be, if this can be done, this has to be done. And if it cannot be done, there will be always a question, whether it interferes with something. So once you study these compactifications, you compactify on arbitrary Riemann surface, okay, with arbitrary values of flux. So if everything works, like if you combine things with various fluxes such that, say, you take a theory with crazy flux, another with a crazy flux, such that if you combine these two theories, the fluxes, say, cancel out and or at least partially, and you expect an enhanced symmetry, you find that symmetry. This is a consistency check. Dualities which are related to pair of pens decompositions, these are more checks. But you are absolutely right. These are not proofs. There always can be a subtlety that will say that, something will not work, and then you will say these dualities are not correct. But it is exactly the same as with any other infrared duality or conformal duality. So it's exactly the same caveats hold here. Yeah. One can look on higher form symmetries. In the examples I have discussed, I don't think there are interesting higher form symmetries, but in other cases, there are. And you can look at them and mapping them and so on.
Okay, I have a question actually. So, so how does this picture, is this picture sort of, can it be related to the story of these 4D n equals to 1 RG flows, which end up at 4D n equals to 2 fixed points? Like, can you basically, like, if you, are there sort of RG flows from each of these conformal duals, let's say, to a 4D equals to 2 theory? Is it possible?
So this is so here we discussed the starting point was 1,0 theory. So on a generic Riemann surface, we only expect to obtain n equal 1 supersymmetric theories in 4 dimensions. So in general, you will not get n equal 2 theories even by deforming these theories. There is another question that you can ask, which I think should be answerable, is that is the following. Let us remain in the realm of classes. That is, we compactify a 2,0 theory on some Riemann surface with some flux and so on. With general value of flux, so let me think about the 2,0 theory as 1,0 theory with global symmetry, which is SU2. And we turn on flux to that SU2. So we obtain a large number of n equal 1 theories. This is the n equal 1 classes. And then the question is, are these Maruyoshi-Song type of Lagrangians, can they be explained in some way, by in this n equal 1 logic? I don't know, but my strong feeling is that there should be, okay? And there should be a way to do that. Like, you start from a theory with some irregular singularity, you obtain exactly the Argyres-Douglas theory in some way, but then there is another way to construct this theory, this geometry, by using n equal 1 blocks, but such that the information is the same. You have the same type of puncture and you have the same type of a Riemann surface. Let me give you an example, maybe. This is an example which is, on one hand, is widely known, on the other hand, is not widely known. Let me add a page here. Okay, so this is the example I want to mention. Let us consider n equals 4 with SU2 gauge group. This is a very special case because it has a Cyberg dual. Okay, the n equals 4 with SU2 gauge group is the same as it's SU2 with 3 adjoints, but you can think of it as SU2 with 3 vectors. So if thinking about it as SU2 with 3 vectors, it has an n equal 1 dual as SO4 theory with 3 vectors plus singlets. So if you wish, this is an IR duality between n equal 1 and n equals 4 theory. You start from this theory, which is basically just 2 SU2s with 3 bifundamentals and some gauge singlet fields. And this theory flows to n equals 4. So this is in the paper by Intriligator and Cyberg from long time ago. Okay. So now the question is, a baby version of the question you ask, can you understand this in classes? Can you understand this duality in classes? And yes, you can. So one way to understand n equals 4 is to compactify the 2,0 theory on a torus with a simple puncture, preserving n equal 2 supersymmetry. And so in this case, you will get n equals 4 plus a decoupled hyper. Okay, but you can construct the same surface not by taking the free trinion, and gluing the 2 punctures in such a way, but you can break it in a different way. You consider a tube, a 3-punctured sphere with a puncture and glue it to a tube theory, but in such a way that the flux associated to this surface and to this surface is the same. Okay. For example, you can think of this having a flux a half, and you can think of this as having, say, flux 1 and flux a minus half. Okay, and then these 2 theories are the same, although the building blocks are different. If you consider what this tube is, it is just a bifundamental of 2 SU2s. This was derived in many papers. And this is just a trifundamental. And you exactly will obtain this type of a duality. So there is this class S explanation of this duality between n equals 4 and an n equal 1 construction of it. And then, of course, you can ask, okay, this is for SU2. Is there a generalization for SUN? This Intriligator Cyberg duality is special to SU2 because vectors are the same as a joint. But in this type of thinking, immediately you have a generalization. It's just you need to construct this theory and this theory for higher n. And it so happens that these theories are non-Lagrangian. They are strongly coupled theories for higher n generalizations. But exactly the same thing works. So to answer your question, in some cases, like here, there is a simple, like very similar story that we can discover. For Argyres-Douglas theories, I don't know of such a story, but I strongly feel that there has to be.
Right.
Okay.
But for 6D 1,0 theories, there can still be like accidental flows that you might have, right? But I guess
yes. So in some cases, actually, we do have accidental global symmetries. In some cases, there might be accidental supersymmetry. I don't have an example in mind now, but there might be. Let me mention another thing, that we have a lot of examples of what I would like to call 6D dualities. Like you start from two different 6D theories and put them on two different Riemann surfaces, and you flow to the same theory in 4 dimensions. Okay. One such example is to take, say, 1,0 theory on a torus, and then you obtain some n equal 2 theory without, you don't turn on any flux. Or you start from some 3 puncture spheres in 2,0, and then you might obtain the same theories. This was discussed by Yuji Omori and friends, and more recently by Lori and other people. And there are many examples of such dualities. 2 different theories, 2 different flows, starting from 2 different 6D theories, giving the same 4D theories. And this can be that, giving same n equal 2 theory or same n equal 1 theory. So there are many dualities of this sort. And understanding this, probably, to understand this systematically, you probably need to embed these constructions in string theory. And like all of my discussion was field theoretic. The string theory was like, we started in 6D with the field theory, and they never went into string theory. But to understand these types of equivalences, you might need go to string theory, and from the point of view of field theory, they will appear as accidental.
Other questions, comments? All right. If not, let's thank Shlomo again.